So my today's topic is about bivariate distribution. I started bivariate distribution in one of my last classes, and I'm going to continue from there. I actually made a chart where two random variables were taken into consideration and their respective probability distribution were found. Now we remember that so as we have discussed univariate distribution and its various properties, and with respect to univariate distribution we discussed about conditional probability based theorem, etc. Everything can be carried forward to the concept of bivariate distribution. Today I'm going to talk about, first of all, I'm going to talk about how to calculate the marginal probabilities in a bivariate distribution, and how to calculate the conditional probability, as well as what is the form of Bayes theorem. Okay, and for the time being, I'm considering only the discrete case. So discrete bivariate random variables x, y are taken into consideration over here. My first definition goes like this: if fxy, x, y is the value of the joint probability distribution, of the discrete random variables x and y at the points x, y, and if fy of y is the value of the marginal distribution of the random variable y at the point y, then the function given by f x given y of x given y is equal to f x y of x, y divided by marginal probability f of y, provided fy of y is not equal to 0 for each x within the range of the random variable capital X, within the range of random variable capital X. This is the definition of the actually, I hope that you can recognize this particular symbol that I have used over here. The symbol stands for the conditional event, as we consider two events, capital A and capital B, and the conditional event is denoted by A given that B has happened. So therefore, consequently, this sort of distribution that I have defined over here is actually called conditional distribution of capital X given capital Y is equal to small y. So this is the definition. And what are these symbols? The symbols are very important. I mean, if you are comfortable, if you are not comfortable with these symbols, then you will be, you may face some problem while solving this type of problems in probability theory. You see that whenever I discuss about joint probabilities like this, f of xy, as you know, this represents the joint probability function. I am using the symbol x, y together. Okay. When I'm talking about the marginal probability only, that means I'm not concerned about capital X now. We want to find out the probability function corresponding to the random variable y, which will be fy. I'm using its mother random variable capital Y as subscript. And when I'm talking about the conditional probability of the type x given y, so in the subscript you see that I have written capital X given capital Y. These are the names for the function, and the points will also take similar kind of shape, which is x given y. These are the points. Small x and small y are the points of these random variables capital X and capital Y respectively for some given range of x and given range of y. So this is the definition of conditional distribution, or you can say the conditional probability distribution of the joint random variable capital X and capital Y, and I'm considering the discrete case only here. And the definition, however, will remain same for the continuous case also. I mean, in continuous case, the definition will not change. What will change is the way of doing the calculation. That will change. Now, similarly, we can also define the conditional probability distribution of capital Y given capital X equal to small x. And if I ask you to find out a similar expression for the same, you can do it very well, easily. What you will do, first of all, I want to find the conditional distribution of y given x. So I will write the mother variable as y given x. This is the name of the function. This is the notation. Its points will be of this type y given x. And you know, probably you can recall that conditional probability P of A given B, this is equal to P of A intersection B by P of B, which comes from the basic axioms of probability. So this can be written as joint probability function capital XY of x comma y given by marginal probability function of capital X. So these are the definitions of the conditional probability distributions of x given y and y given x. Now we shall consider a problem, and first of all, we will try to understand how to calculate the marginal probabilities, because to calculate the conditional probabilities of a joint probability distribution, we need the marginal probabilities. So for which we need to construct the marginal probability first of all. So suppose we have a joint probability distribution which is defined as follows. So I'm going to write the chart of the joint probability distribution first of all. That means I'm giving you the probabilities of this type, fxy of x comma y. Okay, let me prepare the chart first of all. And I always, as you have seen, that I always keep x on the top and y on the left. Now you can reverse the system. You can keep x on the left and y on the top. That is up to you. So if you are doing, I don't know what book you are following, but if you follow the book where x is kept on the left-hand side and y is kept on the right or top, then accordingly your table will change, and that is you have to take kind of transpose of the system. Okay, so be careful about that. So if I write x and y over here, and suppose in my case x takes two values only. For simplicity, I'm considering two values of x only. Say, for example, -1 and +1. And suppose the values of y are also -1 and -1, 0, and +1. I'm taking three values over here, for instance. So the values of y are -1, 0, and +1. Okay. Then suppose the probabilities are given in the following way. Suppose the first probability in this case, is 1/8. This probability is half. This probability is 0. This is 1/4. This is 1/8. And this is 0. I showed you how to calculate the probability by considering a problem of caplets, aspirin and laxative tablet, and painkillers. I considered a problem in my last class. You just go through my video and you will find it out over there. So I told you how to calculate these probabilities. Only thing that you have to keep in mind that this, when I'm talking about 1/8, say, this probability is the value of the random variable xy, joint random variable xy at the point -1 and +1. Achha, just a minute. The call has come. Please, just a minute. Okay, just yeah. Now, so I was talking that as I've written 1/8, that means I'm considering the value of the random variable xy at the point x equal to -1 and y equal to -1. Okay. Similarly, at different points, we have got different probabilities of the random variables. So this is a joint probability that is given to you. Okay, this has been calculated. Keep in mind that in joint probability satisfy the relation. Joint probability satisfy the relation of same type of relation that is satisfied by the univariate distribution. In univariate distribution, when we get all the probabilities, what we do, that we say the total probability is 1. So if you want to check whether the given system, the given chart is a joint probability distribution or not, what we do is that we take the probabilities, we take all the items together, and we take the sum of these items and check whether the sum is 1 or not. So the sum is 1/8 half plus 1/4, 0 plus 0 plus 1/8. So this sum, let me just check whether this is a probability distribution, indeed a probability distribution or not. Otherwise, the many fallacies will appear. So we get 1 plus 4 plus 2 plus 1. So it is 8/8. So this is 1. So yeah, the table on which I'm working is a joint probability distribution. This comes from the total probability law. Now let me talk about the how to calculate the marginal probabilities. I will talk about first of all how to calculate f of fyy and fxx. So first of all, once we prepare this chart, then it is very easy to calculate the conditional probabilities. Okay, so I'm going to the next page and I'm going to show you how to do this. Now it could have been better if I would have drawn this joint probability function in this page, because I need I need some space below the table, but which the space was not there in the previous page. Here I need some space to write something, so I'm rewriting quickly the chart once again so that I can do the calculation. So I have this distribution of points for x and y, and these were the values. So we had 1/8, half, 0, 1/4, 1/8, 0. Okay. And now I am going to calculate the joint probability. Now, what is the formula for calculating? We need some, sorry, I want to calculate the marginal probability. So we need some sort of formula to calculate the marginal probability. So I have to provide you with the formula, first of all. The marginal probability of X, which we denote by marginal probability of the random variable X, which we denote by f of X. This is actually nothing but the sum total of the joint probabilities taken over all possible values of Y. And marginal probability of random variable Y, will be denoted by f of y, which is the sum total of all the joint probabilities taken over all possible values of X. So if you carefully observe at the formula, you will find that your marginal probability of fxx will be on this side, and your marginal probability of fyy will be on the right side. So I will construct the marginal probabilities now with respect to the given formula. So here I am going to write fxx, and here I am going to write fyy. Now look at the formula. First of all, I will calculate fxx. Okay, what it is saying, consider the joint probabilities from the joint probability distribution. You consider the joint probabilities, and you consider only those joint probabilities where y is varying. So here, if I want to calculate the marginal probability for x equal to -1, for here I should write for some x, here I should write for some y. Okay, so for x equal to -1, if I want to calculate the marginal probability, what I need to do is I have to add 1/8, 0 and 1/8. So marginal probability of fxx -1, this would be 1/8 plus 0 plus 1/8, which is 1/4. So here I am going to write 1/4. Okay, and if you want to calculate the marginal probability of fx1, then you are going to consider the second column where y is varying. I'm actually taking the summation over all possible values of y. Just look at the formula, and I will add half 1/4 plus 0, and that would be equal to 3/4. So here I am going to write 3/4. So this is the calculation of the marginal probabilities of this chart, marginal probability of X. Now I'm going to calculate the marginal probability of Y at the point -1. There will be 3 marginal probabilities for Y: at the point -1, at the point 0, and at the point +1. 3 marginal probabilities will be there. And the sum will vary over X, all possible values of X. So what I am going to do, just look at this formula, carefully observe this formula. I am going to take the row for calculating this value. I'm going to take the first row, and I'm going to add I'm going to add 1/8 and half. Okay, so I'm writing over here, this is 1/8 plus half, which is 5/8. For the second one, I'm going to add 0 plus 1/4, so which is 1/4. And for the third one, last one, I'm going to add 1/8 and 0, which is 1/8. Now I will substitute the values over here. So I will write here 5/8. Here I'm going to write 1/4, and here I'm going to write 1/8. Now you see one thing, that you can verify whether your calculation is correct or not by doing a quick check. You add the total marginal probability of X, 1/4 plus 3/4, which is 1. So total marginal probability is 1. You calculate the total marginal probability of y, which is 5 by 8 plus 1 by 4 plus 1 by 8, which is 5 plus 2 plus 1 by 8, that is 8 by 8, which is also 1. So here we are getting the total probability 1, and this is telling with the total probability, total joint probability. In the previous table also, we get the total joint probability 1. When we are calculating the marginal probabilities, you can easily verify whether your calculation is right or wrong by doing this quick check. You calculate the total marginal probability. So summation f of y over y, this total marginal probability will be equal to 1, and total marginal probability fx x, this would also be equal to 1. This is for quick check. You can verify your given result. So now we have calculated the marginal probability of the following given joint probability distribution. Okay, I hope you have understood what my point, how to calculate the marginal probabilities. Now I'm going to show you how to calculate the joint probabilities. Sorry, the conditional probability. So suppose I want to calculate the conditional distribution of capital X given capital Y is equal to -1. Now what is the formula? Just look at the formula. I want to calculate which part? I want to calculate the conditional probability of X given Y equal to -1 at some point Y equal to -1. So here I'm going to apply this formula in a following manner. Just observe. First of all, so I'm going to write like this. I'm going to write the expression first of all, f of X given Y. The point is X given Y. And this is also a kind of chart which we are going to calculate. The values of X is -1. The possible values of X's are -1 and 1. And at the point Y equal to -1, we want to calculate this conditional probabilities. Okay. So for Y equal to -1, that means here I have written small y equal to -1, which is a value. Here I have written capital Y equal to -1. That means the mother variable is taking only one value, that is -1. Given that the random variable Y has taken the value -1, what are the conditional probabilities of this and that? What is the formula? The formula is, I'm again writing the formula for the conditional probability. The formula is as follows. The formula is f of X given Y of X comma Y, which is f of XY XY by f of Y at Y. So if I write the values from the chart, then what will we find? Let us see. What do we want to find over here? We want to find f of X at the point Y equal to -1. Okay, so that means we want to find f of XY at the point X equal to -1 and Y equal to -1 and f of Y at the point -1. This we want to find. So there will be two values actually. One value will be f of XY at the point -1, X equal to -1 for Y equal to -1. That is one value. And another point is f of XY at the point X equal to 1, Y is -1. These two values will be calculated from the table. All the values have already been calculated from the table. We need to substitute them. Now you see, just look at the table that we have constructed above here. Just look at this table. F of XY at the point -1 and 1 is actually 1 by 8. This point is actually 1 by 8. Okay. Divided by f of Y at the point -1, which is f of Y. I have considered this point first of all, and then f of Y at the point -1. That means this point. So we'll write 1 by 8 by 5 by 8. which is of course 1 by 5. This is the first value of the conditional probability. Second value is f of xy at the point 1 and -1. F of xy at the point 1 and -1. So the value is half. And f of y at -1, which is again 5 by 8. So we will write here half by 5 by 8. So which is how much? It is 4 by 5. And you see, again, if I add the conditional probabilities, that these two conditional probability, they are satisfying the total probability loads. 1 by 5 plus 4 by 5 is equal to 1. So this is how we calculate the conditional probability for a given random variable where another random variable is fixed at some point. So conditional for a bivariate, in what happened in univariate case, we got one particular value, fixed value for the conditional probability. In bivariate case, we are getting different values, two different values for the conditional probabilities, because in bivariate system, we have to be careful about the range of the values on which capital X, the domain of the values on which capital X is defined, and domain of the values on which capital Y is defined. Depending upon that, the expressions for conditional probability, marginal probability, these are actually derived. Okay. So I hope you have understood how to calculate this thing, and this is very important. I can see some people, they have joined, gave attendance, and then left. Okay. They are leaving everything for some later part. They will think that they can manage with seeing the videos only. So okay, let it be. Anyways, now let us consider another problem. The problem is as follows. Check whether capital X and capital Y are independent if their joint probability distribution is given by, if the joint probability distribution is given by f of x comma y, xy, this is equal to 1 by 4 for x equal to -1, y equals to -1, then x equal to -1, y equals to 1, then x equal to 1, y equals to -1, then x equal to 1, y equals to 1. Okay, so suppose this is the problem. We want to check the independence. We want to check the independence of the two random variables. We know from our previous knowledge that if capital A and capital B be two events, then probability of A intersection B is equal to probability of A into probability of B if and only if capital A and capital B are independent. Okay. Here the same concept have been generalized. The same concept has been generalized. So first of all, we will look into the joint probability distribution. We'll look into the joint probability distribution, which needs to be found, because for the calculation of, for checking of this independentness. So I am trying to figure out how the joint probability distribution will look like over here. So two random variables x and y are there, putting x on the top and y on the left. I am giving their values. Now, if you look at these values carefully, you will find that the range of x, they are taking discrete values. So the range of x and y are actually -1, 1. These are the points which x and y are taking. So I'm writing for x, I'm writing -1 and 1. For y, I am writing -1 and 1. You know the marginal probabilities will be on the right side for y and at the bottom for x. Okay, so here 1 will be there. So here I'm going to write f of x, x, and here I'm going to write f of y, y. Okay. Now you see for each of these points, x equal to -1 and -1, the probability is what? The probability is 1/4. For x equal to 1 and -1, the probability is 1/4. For x equal to -1 and 1, the probability is 1/4. For x equal to 1 and 1, the probability is 1/4. If I calculate the marginal probability, you know the marginal probability of x for this column will be the sum total of this column. Okay, I have already explained this. So this would be, I'm writing over here, 1/4 plus 1/4, which is half. Half is the value. And here it is also 1/4 plus 1/4, that is half. Column wise, I'm saying. And row wise, we'll get the marginal probabilities of y. So that would be half and that would be half similarly. Okay. Now, if we want to show that x and y are independent here, where x and y actually have a joint probability distribution, then we need to check f of x, y, x comma y. This must be equal to f of x into f of y in parity with this particular definition. Okay. Now you see, if I try to calculate f of x and f of y, if I take the product of these two, carefully observe, since all the points are same over here, all the points in this matrix are same. So for all x and for all y, if I consider this product, we will get half into half. This must happen for all x and for all y. Then only we will say that the two random variables are independent of one another. So f of x into f of y gives you half into half for all x and for all y, which is 1/4. Okay, and not only this, you see that for all x and for all y, if I consider the joint probability distribution, if I consider the joint probability table, it is indeed 1/4. So f of xy for at the point x and y, for all x and all y, that is also 1/4. So what we are getting? We are getting f of x, marginal probability of x at all points, we multiplied by marginal probability of y at all points. This is equal to the joint probability of x and y at all points. And therefore, this implies x and y are independent random variables. Independent joint random variables. Independent joint random variables. Okay. This is one important concept that is actually you have to be very careful of. Okay. Then suppose I'm giving you another problem. I will not be able to do many problems in today's class because the class is too short. So suppose I'm giving you this problem, joint probability distribution of which is f of x, y, x comma y, where x takes the values 0, 1, and 2, and y takes the values 0, 1, and 2. Okay, then suppose the probabilities are 1/6, 1/3, 1/12. Here the probabilities are 2/9, 1/6, and here the probability is 1/36. Suppose the probability is like this. Can you tell me quickly what will be the values for f of y at different points? And what will be the values for f of x at different points? Can you quickly tell me? You quickly calculate this particular thing. And then what you are going to do is that you are going to find the conditional distribution f of x given y. Okay, I'm considering this one. You could have considered f of y given x also. So the probable values are 0, 1, 2, and y is having the value 0, 1, and 2. You are going to calculate this chart. You are going to fill up this chart over here. Okay, this is your task. And lastly, once you finish calculating this particular two tables, your job is to calculate f of y given x, this conditional probability at the point x equal to 1 and y equal to 0. Okay, so you are going to calculate. I'm writing it clearly. I want to, after calculating this particular table, we want to calculate the conditional probability of f of y given x at the point x equal to 1 and y equal to 0. And by the definition of conditional probability, we know what is the definition of conditional probability. F of a given b, this is equal to probability of a intersection probability of b. Okay, and that is given by probability of a intersection b by probability of b. And also we know that this is nothing but probability of b given a into probability of a by probability of b. So which is of course nothing but the Bayes theorem. So you just check this particular thing when you find some time. By definition, if I apply this definition over here, we can write it in the following manner. Just correlate what I am writing. Okay, I'm calculating y by x. Here I have asked you to calculate x. What I am doing? Joint probability fxy is given. Conditional probability fxy is given. These two tables are given. I want to calculate the conditional probability of f of y by x at some point for the point x equal to 1 and y equal to 0. So that means we need the Bayes theorem kind of thing to calculate this. So which can also be done for this bivariate distribution. So just try to correlate that probability of a given b is probability of a intersection b by pb. So I have written here f of y given x is equal to f of xy by fx. Now I am going to break it. Probability of a intersection b is broken in this manner. So I'm going to break the numerator portion also. So I'm going to write it as f of x given y at the point x equal to 1 and y equal to 0. That will be multiplied by f of y at the point y equal to 0 divided by f of x at the point x equal to 1. Okay, now your job is to finish this table after the class. Don't have to rejoin once again because I have another class from 2:30. These are the question marks that I am marking for you. You need to fill this up. You need to fill this particular part. And then from using the table, you have to calculate this particular item. And you will see that this will be equal to 2 by 3. If your calculation is all right, the answer must come as 2 by 3. Okay, so this much I want to, I can discuss in today's class. Tomorrow we'll be having class from 2:30 because I actually requested your CR that I have some problem in the morning. Okay, and therefore I need to take the class in the afternoon session.